Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over both the product and quotient rule for differentiation. So there's more differentiation rules. We've discussed so far the constant rule, the power rule, the constant multiple rule, and the sum rule. Now we're going to discuss the product rule and the quotient rule in this worksheet. And later, we're going to get into the chain rule, implicit differentiation, as well as trig derivatives and a few others. So learning each will continue to make calculating the derivative an easier task, because remember when we were calculating with the limit, that was pretty tedious. But now we have all these techniques to help us take that derivative. So let's first discuss the product rule. Alright, so let's go over the formula. If we're trying to take the derivative with respect to x of some function f of x times some other function g of x. Well, we can't just take the derivative of each and multiply it together like the sum rule. We actually have to do something a little bit different. How this works is we're going to take our first function, f of x, and multiply it by the derivative of g of x, and then that will get added to our second function, g of x, times the derivative of the first function, f of x. And that's the product rule. So our first function times the derivative of the second, plus second times the derivative of the first. So let's look at this with our first example, the derivative of x times x squared plus 3. Well, following our formula, we're going to have our first function, which is x, times the derivative of our second function. So that's the derivative of, we're going to take our second function, x squared plus 3, and find the derivative of that, and then we'll add that to, now you can see that we have our second function, x squared plus 3, times the derivative of our first function, which is the derivative of x. Simplifying this, we'll have x times, what's the derivative of x squared plus 3? Using the power rule and the constant rule, 3 goes to 0, so x squared is going to go to 2x, and then we'll add that to x squared plus 3 times, what's the derivative of x? Simply 1. Now let's simplify. X times 2x is 2x squared, plus 1 times x squared plus 3 is just x squared plus 3. So this simplifies down to, combining those like terms, 3x squared plus 3. Now a quick double check. Let's simplify this first and then take the derivative normally, because if we distribute that in, we'll be taking the derivative of x cubed plus 3x. Taking the derivative of x cubed plus 3x is 3x squared plus 3. So you can see when we distribute it in, we get the same exact answer. So it might have been actually easier just to distribute with this problem, but in some problems it's not going to be. For example, down below we have two binomials multiplied together. Distributing that, we're going to have a lot of different terms. So it might be easier just to go ahead and use that product rule, or think about a polynomial to an even larger degree. Let's say a polynomial with 6 different terms, and then multiplying that by a polynomial with 4 different terms. That's going to be a lot of work trying to expand that out and then take the derivative. That's why the product rule is so useful. And in some cases, we can't even distribute. For example, if we're multiplying 2 trig functions. Sure, if we were multiplying x to x squared, x combined with x squared is x cubed. But what's the sine of x times the cosine of x? There's no way to combine those, so we have to use the product rule. Now the product rule may be a little confusing as far as remembering which derivative to take and which derivative to add, but remember that addition is commutative. So as long as we're taking the derivative of one function and multiplying it to the other function, it doesn't matter the order in which we add those together. I will say a helpful hint is, watch this neat trick. If I have some function x squared plus 4 times 2x cubed minus 5, my first function will be f of x, and my second function I'll go ahead and have as g of x. So my green function is f of x, my blue function is g of x. And just because this says f of x out in front doesn't mean we can't relabel the inner functions. Just remember that our overall function is the combination of those two. So if you wanted to label this maybe as g of x and h of x, that's perfectly okay. For now, I'll go ahead and cover this f of x up so it doesn't get too confusing. So if we write our first function, which is x squared plus 4, we're going to immediately take the derivative of that, because the derivative is used in our formula. We use both the function and the derivative. So I'm going to take that derivative and have it as 2x, because the derivative of x squared plus 4 is 2x. Next, immediately after, I'm going to write g of x, keeping it in line with f of x, and that's going to be 2x cubed minus 5, and then I'm going to take the derivative directly below. So the derivative of 2x cubed minus 5 is going to be 6x squared, bringing that exponent down in front and then decreasing it by 1. So writing it this way is what I like to consider bookkeeping, because I have all my different parts of my product rule. I have f of x, I have f prime of x, I have g of x, and I have g prime of x. I already have calculated all those different parts. And for the product rule, the way in which we write this, I'm just going to draw a cross in between to help me remember. F of x times g prime of x plus g of x times f prime of x. And there we go. As long as you can remember to organize it this way, you're always going to be able to do the product rule. So I'll just write what I did. So my f of x squared plus 4, keeping that in parentheses, times g prime of x, which is 6x squared, plus g of x, which is 2x cubed minus 5, times f prime of x, which is 2x. There we have it. That's my derivative of my function. So if my function was labeled as f of x, that is the complete f prime of x. So just as a note, don't get confused when bookkeeping. This f of x is not the same as this f of x. I split this function into two individual smaller functions so that I could use the product rule. From here, I'll let you do this on your own. Feel free to distribute this out and combine like terms for algebra practice. But to keep the pace on this worksheet, let's move on now to the quotient rule. The quotient rule, again, we can't use it like the sum rule. If we're taking the derivative of some function f of x over some function g of x, we can't just take f prime of x and divide it by g prime of x. That's not going to give us the correct derivative. So this formula is a little trickier than the first, but we have some fun techniques to help us remember it. We're going to take g of x, and that will get multiplied by f prime of x, and then we're going to subtract f of x times g prime of x, and that's all over g of x, that entire function squared. Now you may be looking at this and thinking, how will I memorize this? Here's a fun saying that you may have heard before. Low d high minus high d low all over low squared, or low low. Low d high minus high d low all over low squared. Low meaning our denominator function, so g of x. D high, the derivative of our numerator function, minus, that minus is important, high, our numerator function, d low, times the derivative of our denominator all over low squared. There we have it. Low d high minus high d low all over low squared. So throughout this worksheet, I'll be saying that a lot, as well as how I remember the product rule. Feel free to come up with ways on your own to remember each, if you feel so inclined. But let's get started with that first example. So we're going to do low d high minus high d low all over low squared. So low is x, and then d high, I'm just going to write this as the derivative of my higher function, x squared plus 3. And then we have minus high, which is x squared plus 3, that's my numerator function, d low, so times the derivative of my denominator function, all over low squared, so x squared. Now let's actually finish this out. We have x times the derivative of x squared plus 3 is 2x minus x squared plus 3 times the derivative of x, which is 1. And that's all over x squared. Now this one's going to simplify down a little bit for us. We'll have 2x squared minus x squared plus 3. And remember, this x squared plus 3 should be in parentheses because that entire function is subtracted. And then that's all over x squared. 2x squared minus x squared is going to give me just a single x squared. And then I'll be subtracting 3, and that's all over x squared. Now, for fun, let's simplify this down even further. Because if I split my fraction up, I'll have x squared over x squared, which equals 1. And then I'll have minus 3 over x squared, or 3x to the negative 2. And why I wrote it like this is because we're going to do a quick double check by splitting this fraction and simplifying down first, and then taking the derivative. So, simplifying this, we'll have the derivative of x squared over x is x, and then we're going to be adding that to 3 over x, which I'll write as 3x to the negative 1, so that we can use that power rule. So our derivative is going to equal, the derivative of x is 1, plus the derivative of 3x to the negative 1, bringing that exponent down in front, that's going to be a negative 3x to the, subtracting 1 from our exponent, negative 2. There we have it. Same exact thing. 1 minus 3 over x squared. And again, it might have been easier to actually simplify this down before taking the derivative. However, that's not always going to be the case. Look at that next example we have. There's no way to really split this fraction up because the denominator has multiple terms. So quotient rule is definitely the way to go with this one. And just remember that sometimes you will be able to simplify down and cancel out factors before you start doing the quotient rule, so always double check. In this case, there's nothing that I can pull out or simplify down, so I'm going to do the quotient rule, low d high minus high d low, all over low squared. So low is going to be 2x cubed minus 5, and then d high, that's the derivative of my high. So the derivative of x squared is 2x. And then I'm going to subtract high d low. So my upper function, the function in my numerator, times the derivative of my denominator, the derivative of 2x cubed, is going to be 6x squared. And this is all over my denominator squared. So 2x cubed minus 5 squared. Low d high minus high d low, all over low squared. Now on your own, distribute that numerator through, combine like terms, and simplify as far as you can go. But let's continue on for now. Example 1, we're going to find the equation of the tangent line to the following functions at the given a values. So remember, the derivative tells us the slope of the tangent line, and once we have that slope, we just need a point to make a line. So let's go ahead and calculate the slope. And the slope is taking that derivative. So I need to take the derivative and then plug my a value in to find the slope at that point. So f of x is this, my f prime of x is going to be, well, let's do that trick. Let's write out my different functions. So I'll write out f of x as 3x squared plus 4. And remember, this f of x is not the same as my original function. I'm just using this for bookkeeping. So I write my f of x function. Now I'm going to write my g of x function next to that, which is my other function in my original, 2x minus 4. Now I'm going to take the derivatives of each. F prime of x is going to equal 6x, and g prime of x is going to equal 2. Now, go ahead and draw that cross in between. So we know overall that our f prime of x is going to equal first times the derivative of the second, so that's 3x squared plus 4 times the derivative of our second, which was 2, plus second 2x minus 4 times the derivative of our first, 6x. So I definitely recommend bookkeeping until you get the pattern down, and then you can do a lot of it in your head. First times the derivative of the second plus second times the derivative of the first. Simplifying this down, 3x squared plus 4 times 2 is going to give me 6x squared plus 8, and then I'll add that to, distributing the 6x through, that's going to be 12x squared minus 24x. Simplifying this down even further, combining like terms, that'll be 18x squared minus 24x plus 8. So that is my derivative of my function, but I want to find the equation of the tangent line. So if I have my derivative function, in order to find the slope at a point, I plug in the point in question. So my point is a equals 0. Plugging a equals 0 on in, I'll do f prime of 0. That's going to be 18 times 0 squared minus 24 times 0 plus 8, which is going to give me 8. So I know my slope is 8. To make a line, I need a slope and a point. So I have my slope. Now I just got to use my point. So if my x value is 0, my point is 0, f of 0. So that's going to be plugging 0 into my function. So I'll get 0, comma, if I plug 0 into my original function, 3 times 0 squared goes to 0, plus 4, so I have 4 times 2 times 0, that goes away, and I'll be left with a negative 4. So 4 times negative 4 is going to give me a negative 16. So my function value at 0 is negative 16. Let's go ahead and put this in point slope form. Y minus y1, so that's going to be y plus 16 equals our slope m of 8 times x minus x1, x minus 0. And there's my point slope form. Feel free to simplify this down or write it in slope intercept form. Now moving on to part B, we're going to need to use the quotient rule in order to find that derivative. And once we get the derivative, we'll plug in our a value to find the slope at that point, and then also plug a back into the original function to find the overall point, slope, point. We can then make a line. So starting with the derivative, dy dx, we're going to have low, remembering the quotient rule, x cubed plus 5, d high, the derivative of my high is 6, minus high, 6x minus 7, d low, the derivative of my low is 3x squared, and that's all over x cubed plus 5 squared. Now I want to find the derivative when a equals negative 1. So I can simplify this down, but I'm plugging in a point anyway, so let's just go ahead and plug it in. So I'm going to have negative 1 cubed plus 5 times 6 minus 6 times 1 minus 7, and remember that's a negative 1, so 6 times negative 1 minus 7 times 3 times negative 1 squared all over negative 1 cubed plus 5 squared. All right, so let's do out this math. If we have a negative 1 cubed is a negative 1. When we add that to 5, we get 4. 4 times 6 gives us 24, and then we'll subtract negative 6, because 6 times negative 1 is negative 6, minus 7 gives us a negative 13. And then we're going to multiply that by 3 times negative 1 squared is going to be 3 times 1, which is 3. Negative 13 times 3 is going to give us a negative 39. But if we have 24 and we're subtracting a negative 39, that's going to be 24 plus 39. And that's all over negative 1 cubed is a negative 1, plus 5 is 4, 4 squared is 16. 24 plus 39 is 63, and that's all over 16. And this doesn't really simplify down, so 63 over 16 is our slope at that point A equals -1. So now that we have our slope of 63/16, we're now going to find that point. So I need to find f of -1, essentially when I plug in -1. So if I have 6 times -1 minus 7 all over -1 cubed plus 5, well, we can see that 6 times -1 is a -6, minus 7 gives me a -13, and that's all over -1 cubed is a -1, plus 5 gives me a +4. So my point is -1, -13 fourths. So writing the equation of the tangent line, we'll have y minus y1, so y plus 13 over 4 equals m, our slope, which remember, 63 over 16, times x minus x1, x minus -1, so x plus 1. And there we have it. That's the equation of our tangent line at the point when x, or a, equals -1. So now that we've gone over finding tangent lines, let's practice just finding derivatives. So in example 2, we're going to be evaluating the following. Let's find the derivative with respect to x of 3 over x to the 6th. Low d high minus high d low all over low squared. Quotient rule. We're going to get x to the 6th times the derivative with respect to x of 3 minus high 3 times the derivative with respect to x of our low all over low squared. X to the 6th squared. Simplifying this down, we'll get x to the 6th times 0 minus 3 times the derivative of x to the 6th is 6x to the 5th, and that's all over x to the 6th squared. Algebra, multiply those exponents, so x to the 12th. This is equal to -18 x to the 5th over x to the 12th, which we can simplify because x to the 5th over x to the 12th is going to be -18 over x to the 7th. Now for this one, quick double check, we didn't really even need to use the quotient rule because we could have just rewrote this as a negative exponent and used the power rule. Think about taking the derivative of 3x to the -6th, same exact thing, just rewrote it. That's going to be -6 times 3, which is -18, and then we decrease that exponent by 1, so that brings us down to -7. -18x to the -7, or -18 over x to the 7th. Those are equivalent, so it doesn't matter which way we take the derivative. But this is just good practice. Let's move on to part B. In part B, we're taking the derivative with respect to x. This is going to be a good product rule. First times the derivative of the second plus second times the derivative of the first. Doing some bookkeeping, I'm going to write f of x, which is my first function. So that's going to be x squared plus 4x minus 1. And then I'm going to write g of x, which is my second function, x cubed plus 5. Now I'm going to take each of those derivatives. So the derivative of f of x is going to be 2x plus 4. And the derivative of g of x is going to be 3x squared. And if you're confused as I'm taking derivatives for these simple polynomial functions, please refer back to that previous example worksheet where we did some practice with the basic rules of differentiation. The constant rule, the power rule, the constant multiple rule, and the sum rules. Those will be helpful for taking derivatives. So I recommend practicing those even if you think you don't need extra practice. So for the product rule, next step, draw that cross in between. So we're going to have x squared plus 4x minus 1 times 3x squared plus x cubed plus 5 times 2x plus 4. And there we have it. That's our derivative with respect to x. Now, I definitely recommend simplifying this down, but for the sake of time, I'm going to continue on. However, on your own, distribute this out, combine like terms, and simplify this derivative down. I just want to walk through the motions of doing the product rule with you so that you're prepared when you get into more complicated problems. The algebra, though, do that on your own for extra practice. For C, this is a good quotient rule. Low d high minus high d low all over low squared. So low is t minus 1. Derivative of my high is going to be 2t minus high, which is t squared, so my numerator, times the derivative of my low. The derivative of t minus 1 is 1. So the derivative of my denominator is 1, and this is all over t minus 1 squared. Simplifying this to make it look a little neater, t minus 1 times 2t is going to be 2t squared minus 2t, and then I'm subtracting a t squared from that. And that's all over t minus 1, that entire denominator was squared. Combining like terms, 2t squared minus t squared is going to leave me with t squared, and then I'm subtracting 2t, and that's all over t minus 1 squared. Moving on to part D, we're going to do first times the derivative of the second plus second times the derivative of the first. A little bit of product rule. So, bookkeeping, I'll first write my f of x, 3x to the fifth minus 6x squared plus x. That's going to be my first function. My second function, g of x, is going to be that 4x cubed plus 2x minus 8. Now, taking the derivatives of each, because once I do that, I'll have all my different parts for my problem. I'll just have to write it out. So taking the derivative of 3x to the fifth minus 6x squared plus x, that's going to leave me with 15x to the fourth minus 12x plus 1. And again, feel free to review those previous example worksheets if you're struggling with taking the derivatives of polynomials. Now, for g of x, that derivative is going to be 12x squared plus 2. So here we have it. Our derivative of our entire function is going to be 3x to the fifth minus 6x squared plus x times 12x squared plus 2, and we're going to add that to 4x cubed plus 2x minus 8 times 15x to the fourth minus 12x plus 1. And that's our derivative in this problem. It still looks a little messy, so do some algebra and simplify it down. Let's continue on, now that you've simplified that down on your own, moving on to part E. In part E, we're taking the derivative with respect to r. But the same rules apply regardless of the variable. You can see that I only have r's in my function, and I'm taking the derivative with respect to r, so we're going to treat this just like all of our other problems. We're going to do the product rule because we have one function times another function. Now, I'm going to work through this one in my head without doing the bookkeeping. But I recommend, until you get the hang of this, to write down f of x, g of x, and then those derivatives. That way you have everything on your paper and you're set. So I'm going to have first, which is 5r to the seventh minus 3 times derivative of my second. So times that g prime, which is going to be 6r squared plus 8. And then I'm going to add that to my second, which is 2r cubed plus 8r plus 6 times the derivative of my first, which is going to be 35r to the sixth. You can see first times the derivative of the second plus second times the derivative of the first. And again, simplify this down on your own. Moving on to part F, we're going to take the derivative with respect to y. Y is our only variable in our function, and we're taking the derivative with respect to it. So let's go ahead and use those same methods. And this is going to be the quotient rule. So low, our lower function, our function in our denominator, y minus 1, times the derivative of our high, the derivative of our numerator, which is going to be 2y minus 3. And I'm going to subtract. We're always subtracting between those two separate terms in our numerator. That's going to be high, which is y squared minus 3y plus 2, times the derivative of our low. The derivative of y minus 1 is simply 1. And that's all over low squared, y minus 1 squared. That denominator squared. Now these ones usually simplify down pretty nicely and don't take too long, so let's do it together. Y minus 1 times 2y minus 3. Distributing that binomial through, that's going to be 2y squared minus 3y minus 2y plus 3. And from that, I'm subtracting that entire function, 1 times that entire function. So I'm subtracting y squared, I'm subtracting a negative 3y, so adding 3y, and then I'm subtracting 2. And this is all over y minus 1 squared. Let's continue to simplify this down by combining like terms. 2y squared can be combined with this negative y squared to give me a y squared, and then I'll be subtracting. I have 3y and another 2y, both subtracted, so that's a negative 5y, except then I'm adding 3y to that. So really, this 3y cancels out with this 3y to leave me with just a negative 2y. So minus 2y, and then 3 minus 2, that's going to be 1. And this is all over y minus 1, that quantity squared. But look at this. What multiplies to give me 1 and adds to give me a negative 2? That's going to be y minus 1 and y minus 1. So y minus 1 times y minus 1 all over y minus 1 squared. Look at this. This is just all equal to 1 because my y minus 1's cancel out with the y minus 1 squared in the denominator. So my solution for this derivative is just 1. So my derivative is constant, which means if my derivative was constant, that this original function actually is a linear equation. Because if it's a linear equation, that slope is always the same, so the slope is always constant. Ah, look at this. If we're taking the derivative with respect to y, let's factor that numerator first. What multiplies to give us 2 and adds to give us a negative 3, that is going to be y minus 1 times y minus 2. And that's all over y minus 1. Look what happens. That y minus 1 will cancel out. So this, where it's simply taking the derivative of y minus 2, which the derivative of y minus 2 is 1. So in this case, actually not doing the quotient rule and simplifying down first was easier. So I recommend always double checking to avoid all this work. However, sometimes it's unavoidable. Continuing on, for our last bit, we're going to look at products within products and quotients. So what exactly is a product within a product or a product within a quotient? Well, if we think about it, how do we solve if we have a product of more than just two functions? Let's say that we have a function times a function times a function, 3 different polynomials multiplied together. Or how do we solve if we have 2 polynomials multiplied together in either a numerator or denominator of some quotient? Well, we're going to continue to apply the rules from above. We're just going to have a little bit more work. So here are some more advanced derivatives. Let's get into it. For example 3, our function is equal to x cubed plus 2x times 4x cubed minus 5x times 6x plus 1. This is 3 separate functions multiplied together. But we're going to apply that product rule, but we can only apply it between 2 functions. So I'm going to say that these 2 functions are going to be multiplied by this last function. So doing my bookkeeping, I'm going to say that my f of x is equal to, let me leave myself some more room because this is kind of a lengthy problem, but don't worry, we're not going to even bother with simplifying it down. I'll let you do that on your own. My f of x is going to be x cubed plus 2x times 4x cubed minus 5x. And my g of x is going to be 6x plus 1. So we can easily take g prime of x. G prime of x is simply going to be 6. But how do we find f prime of x? Well, we're going to need to do another product rule to find that derivative. Let's do some more bookkeeping. If my first function in this case is x cubed plus 2x, and my second function, g of x, is 4x cubed minus 5x, then I'll take the derivatives of each of those. The derivative of x cubed plus 2x is 3x squared plus 2, and the derivative of 4x cubed minus 5x is 12x squared minus 5. So now I have my derivative, my f prime of x in my first product rule is going to be, just simply cross these. It's going to be x cubed plus 2x times 12x squared minus 5 plus 4x cubed minus 5x times 3x squared plus 2. So you can see I did the product rule within a product, but my overall derivative, my derivative of my original function, I just need to do first times the derivative of the second plus second times the derivative of the first. This is that entire first function, combining those 2 polynomials together, that is its derivative. So you see we did the product rule within the product rule. And again, that was first times the derivative of the second plus second times the derivative of that first, where we split up that function. So now let's write this all out. I'll go ahead. I want you to leave your work on the page, but just so this doesn't get too confusing, I'm going to erase this. So now we're going to do f of x times g prime of x plus g of x times f prime of x. So I have x cubed plus 2x times 4x cubed minus 5x. That was my first function, multiplied by the derivative of my second function. That's 6x plus 1. That derivative was 6, plus my second function, 6x plus 1, times the derivative of that first function, which was those 2 polynomials combined. That's where my second product rule came into play. So I need a large parenthesis to make sure that I include everything in that f prime of x within that parenthesis. So it'll be x cubed plus 2x times 12x squared minus 5 plus 4x cubed minus 5x times 3x squared plus 2. And I almost fit it in, but I'll zoom out just a little bit so you can see that clearer. And remember, it's g of x times f prime of x. So I need to have parentheses outside that because that g of x gets multiplied to everything. And that's our derivative in part A. I'm not going to worry about simplifying this down for the sake of time, but that's how you would do the product rule when you have a product within a product. And really, we could have had another polynomial here. We could have just made this entire thing as g of x. So then we would have had another product within that product, but there's not just that one way to split it up. We could have also split it up as this being f of x and this being g of x. Or I could have had this as f of x and the circled polynomials as g of x. There are many different ways to split this up, but the results will all be equivalent when you take those derivatives. Let's continue on to part B, our last example on this worksheet. And this is the case of where we have a product within the quotient rule. So let's write out that quotient rule. When we take the derivative of y with respect to x, we do low x cubed minus 6x d high, so I'm going to take the derivative with respect to x of x cubed minus 3x plus 2 times x minus 5. So low d high minus high, so that's going to be x cubed minus 3x plus 2 times x minus 5. And I'm going to make sure that I have parentheses around this. And then that gets multiplied by d low, so the derivative of my low, which will be the derivative of that lower function, x cubed minus 6x. And this is all over low squared. X cubed minus 6x, that entire denominator squared. So I know this is a lot, but stick with me, we're going to do this together. So dy dx is going to equal x cubed minus 6x times the derivative of, this is a product rule here. So feel free to write your bookkeeping, but I'm just going to talk it out and do that in my head. So we're going to have our lower function times the derivative of our numerator, which is going to be first x cubed minus 3x plus 2 times the derivative of our second, which is going to be 1, plus second x minus 5 times the derivative of that first, which is going to be 3x squared minus 3. So again, low times d high. The derivative of my high was first times the derivative of my second, plus second times the derivative of my first. So that altogether is my low d high, and I have to subtract my high, which is x cubed minus 3x plus 2 times x minus 5, and that gets multiplied by the derivative of my low. Here's my higher function, times the derivative of my lower function, which the derivative of x cubed minus 6x is going to be 3x squared minus 6. And that's all over low squared. X cubed minus 6x, that entire quantity squared. And that is my derivative. Low d high minus high d low, all over low squared. So walking through it one more time, my lower function times the derivative of my numerator, which was calculated using the product rule, and then I'm subtracting my numerator function times the derivative of my denominator, and that's all over my denominator squared, x cubed minus 6x squared. And with that, we wrap up the worksheet on the product and quotient rule for differentiation. So now you have at least 6 rules that you can apply for taking the derivative. And be thankful for those rules, because think about the other way we used to take the derivative. That was by using limits. Can you envision taking the limit of this as h approaches 0 of f of x plus h minus f of x all over h? That would be pretty tedious. So even though this looks like a lot of work, it's a lot less work than it would have been if we didn't have these nice rules to apply. So now, once you've practiced a couple more problems with the product rule and quotient rule, continue on to the next example worksheet, where we'll go over the 6 basic trigonometric derivatives and apply all of our rules we now know to those trig derivatives. So until the next video, good luck with your online learning.